Hello. This is the third in a series of 3 short presentations about control over wireless using the ISA 100.11a standard. I am Jay Werb, Technical Director from the ISA 100 Wireless Compliance Institute. The goal of these presentations is to explain how systems based on the ISA 100.11a standard can be used for control. This presentation focuses on network design considerations for control using ISA 100.11a systems. As a review, let's start with a graphic repeated from the second presentation. Here, we suggest that something on the order of 1 second latency, end-to-end, should be the basic performance reference for control. Some applications can manage with less performance, and a few may need better performance. But we have found that a system designed to deliver 1 second latency covers a reasonable range of applications without involving painful user trade-offs. For example, consider human-in-the-loop control applications, shown here as a person pressing a button. Normally, users want to see some feedback from their actions. It's well known that when response time exceeds 2 seconds, the user's attention will start to drift. So we suggest 1 to 2 seconds, end-to-end, as a reasonable target for human-in-the-loop control. As another example, consider automated control, shown here as a pressure sensor feeding data to a valve controller. Generally, the scan period shown should be some fraction of the lag in the process response. We give a value here of 5% as a rough rule of thumb, with plus or minus to indicate that the actual value depends on the application. With that introduction, let's look at some network architectures and how they match up with the requirement latency of something like once every second. Good. We'll begin with a figure that you might already be familiar with, which is a basic reference diagram found in the ISA 100.11a standard. On the right, we have a plant network domain with a control system. The plant network is shown as connected to redundant ISA 100.11a gateways. In the middle, we have the IP backbone domain. The backbone provides coherent network services to the plant through access points that are called backbone routers. The backbone might itself be wireless, such as a high-performance Wi-Fi mesh. On the left, we have a device mesh domain. This is the mesh network of battery-powered field devices. Those of you with some mesh networking experience will immediately recognize that the device's connection to the plant network tends to degrade as you move farther to the left of this diagram, away from the backbone. Here we show the same picture, pointing out that ISA 100 was careful to show 2 devices, especially designated as I/O devices, with redundant backbone connection. ISA 100 included various features to optimize connections in this particular configuration. The mesh network operates behind those devices, but the circled control devices get special attention within the system architecture and in the standard. ISA 100.11a includes various optimizations for the circled configuration. I'd like to discuss 2 in particular. Duocast is an optimization where one message is received by multiple backbone routers and then acknowledged by each in turn. This provides a very high probability that a message will be received by the backbone on the first transmission. Combined with Duocast retries, the control device can be configured for low latency and high reliability. A more fundamental ISA 100 optimization is the architecture of the network itself. The ISA 100 network standard was designed to be a plant-wide resource, not dozens of little networks with hundreds of little edge conditions. If the network is designed optimally for control, wireless devices everywhere in the plant should be able to find at least 1 clear shot at the backbone, and preferably 2 or more. This slide shows the same idea, but using a graphic that focuses more on control aspects. A pressure gauge is shown feeding data into an ISA 100 backbone through a gateway and to a controller. The controller then sends data back to a positioner using the same network. We show both control devices with redundant wireless connections to the backbone. Our main point can be seen at the bottom of the diagram, where we show approximate latency. The backbone network should run relatively quickly, at a fraction of a second. A direct wireless connection to the backbone may involve some significant latency, shown here as about 1 second. This diagram shows that the network is also used for monitoring and control at the same time. The monitoring function shouldn't interfere with the control function. Basically, control should have higher priority than monitoring, as in a real ISA 100 system. The gray clouds located on the left of the wireless network used for control represent a mesh network of wireless devices used for monitoring purposes. Control and monitoring are part of the same network, with control having priority. This slide shows what happens when the layout of your network involves transmitting control messages through a mesh network. If your message needs to propagate all the way through the mesh to get to the controller, and then propagate all the way back along essentially the same path, that can take a long time, for example, 10 seconds in each direction. It is theoretically possible to align all of the planets and shorten that latency, but I think it's fair to say that most battery-powered mesh networks of this kind are not designed to complete this round trip in 1 second. You can compare the network to a highway. The high-speed IP network on the backbone is like a highway. The connection from the device mesh to the backbone is like an on-ramp, one of those with a traffic light during rush hour. You can think of the device mesh as city streets with a traffic light on each corner. There are good reasons to avoid transmitting control data frequently through a battery-powered mesh network. Energy consumption is typically the most important restriction. Devices on the mesh need to sleep most of the time to conserve their batteries. For that reason, we show performance on the device mesh being in the range of 10 seconds, mostly due to the need to preserve battery power in the routing devices. As a rough rule of thumb, if your mesh needs faster response time than 5 to 10 seconds, you need to put extra energy in that mesh repeater somehow, such as providing external DC powers to the repeaters that carry control messages. To summarize the point of this slide, if your control data can be in an unknown state for something like 10 seconds, then perhaps you can use a device mesh for control. And this configuration is fully supported by ISA 100.11a. But what if you need a mesh configuration and your control application requires fresh data, say every 2 seconds? One solution, of course, is peer-to-peer networking, as shown in this slide. I haven't seen this in any products yet, but it's there in the standard. The input block and output block might both be remote from a controller, but they are typically close to each other. In many cases, they can establish a direct wireless connection that is strong and reliable. You can also arrange to bounce the signal through a single mesh hop for redundant configuration, as shown. In a configuration like this, 1 second is a reasonable target as shown in the diagram, and the result is both efficient and effective. One advantage of this approach is that the connection and control algorithms continue working even if there is an interruption in service in remote components. A peer-to-peer connection of this kind also implies that the control logic runs in the devices. ISA 100 anticipates that with its application objects that are similar to foundation field bus blocks, but simplified for wireless. The result is a fully functional peer-to-peer connection that can do useful work without a real-time link to a remote controller, as shown in this picture. Okay, skip that slide. And skip that slide. To summarize, we show three options that are supported by ISA 100.11a networks for control. Most of the time, you will be able to arrange redundant backbone connections, shown in the upper left. When that is impossible, you can arrange a direct connection between devices, as shown in the upper right. When performance requirements can be measured in something like 10 seconds, you can transmit data through the mesh network, as shown in the bottom of the slide. When you look at actual ISA 100 systems, you will see these considerations in their basic DNA. The performance you need for control is available in the same scalable architecture that can handle an extensive number of devices used for process monitoring. The structure of the standard makes it all play together, keeping all of these diverse requirements in balance. This completes the third of our short presentations about using ISA 100.11a for control. Thank you for joining us, and have a great day.